So far in this module, we've discussed 2 of our 5 major senses, vision and hearing. In this video, we'll cover the remaining senses, taste, smell, and touch. Taste and smell are senses that both detect chemicals in the environment, such as in the air and in our food. For this reason, they're collectively referred to as our chemical senses. Taste and smell are also highly related. Have you ever had a cold that stopped up your nose and found that suddenly food lost much of its taste as well? You can try this yourself even if you aren't sick. Try plugging your nose the next time you eat something and see if your taste for it also changes. Let's start by talking a bit more about our sense of smell, or olfaction. The nose is the primary organ of our olfactory system. At the top of the nose, in the mucous membrane, are located special receptor cells. When odor molecules enter the nose, they dissolve in the mucus and then interact with small hair-like extensions on these receptor cells. You have many different types of these receptor cells in your nose, each of which is designed to pick up on a single different molecule. Different kinds of molecules, in turn, correspond to different smells. Once an odor molecule has bound to a given receptor, it results in chemical changes that start an action potential. This information can then be sent to the olfactory bulb located at the tip of the frontal lobe, where it can be processed further. Moving on to taste, or gustation. The primary sensory organ of our gustatory system is the tongue. We can perceive taste because of receptor cells that line the surface of our tongue and throat. Groupings of these taste receptor cells are called taste buds. When we eat, say, a delicious pizza, molecules from the crust, cheese, and different toppings dissolve into our saliva. These molecules then interact with our taste receptor cells, causing an action potential that can then send information via different nerve cells to our brains for processing. Different taste receptor cells are sensitive to different categories of taste. For example, some taste receptor cells are specially designed to interact with molecules that we perceive as sweet, whereas other receptor cells are specially designed to interact with molecules that we perceive as salty. In total, scientists now think that there are at least 5 different taste categories that we can perceive: sweet, salty, sour, bitter, and umami, which is a Japanese word that roughly means yummy and is associated with the meaty flavors that you might find in foods such as mushrooms, tomatoes, and of course, meat. You might be wondering about another quality of some foods that I didn't mention, spicy. Is spicy a taste group? Actually, it's not. It's a feeling of pain. We have special thermoreceptors on our skin and on our tongues that are designed to detect temperature. In the tongue, these thermoreceptors can help us perceive when foods are too hot to eat, literally, and might burn our tongues. The kind of hot we call spicy isn't caused by the temperature of foods, however, although it's probably no coincidence that we use the same word to describe the sensation. It turns out that the active ingredient in spicy foods, capsaicin, also binds to these thermoreceptors. This causes the sensation of eating a food that is painfully hot, even though in this case the heat we perceive is not actually caused by the temperature of the food. For more information on our gustatory and olfactory systems, you can check out the supplemental crash course video on Canvas. The final sense that we'll discuss in this module is our sense of touch. Related to touch, I'll also discuss our experience of physical pain. Touch is perceived through different mechanoreceptors distributed throughout the skin. They're called mechanoreceptors because they're designed to detect mechanical pressure. Once activated, these mechanoreceptors can start an action potential, thus converting that mechanical pressure into electrical signals that can be processed by your nervous system. Remember from our previous module that sensory information from our peripheral nervous system travels first to the spinal cord, where it is then relayed up to the brain. Ultimately, the sensory information reaches the somatosensory cortex, a region of the brain in the parietal lobe shown here in blue. Each segment of the somatosensory cortex receives sensory input from a different single part of the body. For example, one segment receives sensory information about your right arm, another about your lips, another about your right index finger, etc. Remember also our principle of contralateralization. The somatosensory cortex on the right hemisphere of your brain corresponds to sensory input from the left half of your body, and vice versa. The sensation of petting a soft dog or holding the hand of a loved one are certainly pleasant experiences of touch. However, what about less pleasant sensations, such as when you burn your hand, stub your toe, or twist your ankle? In short, how does our body perceive what we feel as pain? First, it's worth noting that pain can come in a few different forms. Nociceptive pain is caused by external stimuli that approach or exceed a harmful intensity, like a noise that is too loud, an oven that is too hot, or a touch that is too hard. Nociceptive pain is registered by special sensory nerve fibers, called nociceptors, that are triggered when these potentially harmful conditions are reached, thus alerting your brain to the potential danger. Neuropathic pain, in contrast, is caused by damage to your actual nerve cells and can affect any part of your peripheral or central nervous system. Neuropathic pain is often described as tingling, electrical, or stabbing. It's also the kind of pain you experience when you bump your so-called funny bone on your elbow. Although it might initially sound nice to never experience any physical pain, think for a minute about what this would mean. If you burned your hand, you wouldn't know to pull it back. If you twisted your ankle, you wouldn't know to rest and elevate it. In short, pain is our body's danger alert system, and it's actually helpful. In fact, there are some people born with a very rare condition called congenital analgesia. The nociceptors of these individuals do not function properly, so they never experience or perceive physical pain. Rather than being a wholly good thing, however, these individuals often have shorter lifespans and are very prone to severe injuries and accidents, precisely because they can't respond appropriately to dangers in the environment. On the other end of the spectrum, some individuals deal with chronic, sometimes debilitating pain. While the nature of chronic pain is still somewhat poorly understood, it is an area of increasing interest and research in the medical field. Some people use medications to help relieve chronic pain. For example, opioids are a class of medications that block pain receptors in the brain and spinal cord. While these medications can help with pain management, we now also know that they can be highly addictive as well. Like other drugs, people can also develop a tolerance to opioids over time, meaning that the person needs to continue taking higher and higher doses in order to experience the same level of pain relief. If you'd like more technical information on exactly how opioids are thought to reduce our experience of pain, you can check out the supplemental 2-minute neuroscience video on Canvas. Our perceptions of pain can also be influenced by our psychological state and expectations. This doesn't in any way mean that someone's pain is all in their head, only that our perception of pain, just like our other senses, involves both bottom-up and top-down processes. As a result, just like our brain can be tricked by optical illusions, your brain's perception of pain can also be tricked or altered to some degree. For example, there's some evidence that patients who have to undergo a painful procedure, like having wound dressings changed, experience less pain when they play an engrossing virtual reality game in addition to taking their regular pain meds. Additionally, one interesting study found that holding a loved one's hand can reduce our psychological experience of pain. Specifically, women in this study reported mild shocks as being less painful when they held the hand of their spouse versus a male experimenter or no hand at all. Another fascinating example of the top-down nature of pain perception is the phenomenon known as phantom limb, which frequently occurs in individuals who have lost a limb or other body part. With phantom limb, the person continues to experience sensations, sometimes painful, from the missing limb. How can the brain continue to perceive pain from a limb that no longer exists? Scientists don't really know for sure, but for a video that explains phantom limb pain in a bit more detail, as well as a couple potential explanations of why it might occur, you can check out the supplemental video on Canvas. In this video, we covered our sense of taste, smell, and touch. Related to touch, we also talked about our perception of physical pain. For the exam, you should be able to describe how chemicals in the air and food can be converted into electrical signals, allowing our brains to perceive taste and smell. Describe how our brain perceives touch. Describe how our brain perceives pain, and discuss how this involves both bottom-up and top-down processes.